Hello everyone. Today we're going to start with our first simulation. It's a laminar pipe simulation, and it's a three-dimensional simulation. It only involves flow, so there is no heat transfer in here. You see the problem here, and also it has been uploaded to the portal, so you can perform it by yourself. In addition to the movie that I'm creating now, you're going to have access also to the user guide, which is the step-by-step system of this. So the pipe is an 8-meter long pipe and 0.2 meter in diameter. And we want to simulate the flow inside the pipe, and we're going to start by creating the geometry. So you go to the remote desktop, open ANSYS Workbench, and get one fluid flow fluent and drop it on the location. So the first part would be creating the geometry. And as you remember, you right click on the geometry and choose design modeler. Before I go to design modeler, let me show you something here. Always you can have a look at the property in here. You see, so right click on the geometry and the property, click the property. You will see here different settings for geometry modeling software. The most important part is this one. If you are doing a 3D or 2D analysis, put it on the corresponding dimensions. If you are doing a 2D simulation, 2D geometry, it's fine. You can do it in 3D, but it's always better to choose the corresponding dimensions. So we open our design modeler. The way we're going to create this geometry is we're going to have a circle in our XY plane. So select the XY plane in here. And always when you are selecting a plane, of course, you can rotate this and show different aspect of it. Okay. But one thing you can do is, if you want to look into the plane of XY, just select XY, and then you see this on top, the guy looking on top left right hand side, the guy looking at the plane. Just click on it and we'll show you the plane itself. So we're gonna create a sketch on XY plane. Let me make sure we are recording. Yes, show recorder. Yes, actually we are recording. Okay, so I'm gonna keep the recorder here just to make sure everything is being recorded. And okay, so we select the XY plane, then we go on XY plane, right click on XY plane, and you see this thing on top in here, which I'm rotating the mouse, revolving the mouse around it. If you push this, it's going to create a sketch on XY plane. And remember, guys, and a sketch is just an empty sheet, a white paper that you can draw on it. Then in here you go on to sketching, and what we want to sketch in here is a circle, right? It's the base for our cylinder. So you select circle. Then when you come here, let me see how, oh, oops, I made a mistake. Sorry, that's not the one. So I want to delete that. You click, right click, and delete. What I want to do is, let me zoom in here. Okay, what I want to show you, and guys, usually speaking, if you are in front of your own computer directly, by the gestures of your mouse, you can zoom in, rotate, so on and so forth. But in here, since we are doing through remote, you have to use these buttons on top. So what I want to show you is, when I'm creating circle, when I select the circle, you see the cursor is converted to a pen. Now, if you look at my pen, if I go on the axis, it writes C. So whenever it writes C, it means I'm on one of the axes. Now I want to put the center of the circle on the center of the coordinate. So I go here, you see it becomes P. So as soon as I'm on the center of coordinates, I put P in here. But before doing that, it was 0.2 meter, right? So, and make sure the units, guys, I forgot to say this. Make sure the units are on the units that you want it to be. So we are on meter, we're fine. Then let's create our circle from center of the coordinate. Good enough. And remember, in here we first draw whatever we want, then give it a dimension. So we go to the dimension tab, select the circle, and here it has to be 0.2 meters. So let's zoom in and show it to you. And guys, you see I can zoom in and zoom out, see, with the plus and minus. But if I'm too much zoomed in and too much zoomed out and I lost the big picture, this icon in here, this icon which says zoom to fit, if you push that one, it's gonna bring everything into perspective. Now, what I want to do is, I have my circle in here, so the next step would be creating my cylinder. For that, I will basically use extrude and extrude this in Z positive direction. So what I'm gonna do is I'm gonna extrude this, oops, in Z positive direction, which is this direction. So I push extrude, and once I push extrude, if you see here, the sketch one as our base geometry is selected, and you see it shows in here the projection of what's gonna happen. Then the length is 8 meter, so I put in here 8 meter. And remember, I should push generate. You see in generate in here, so I push generate and it creates my geometry. Whenever you perform any operation in ANSYS, you gotta remember, okay, let me show the recorder. Okay, whenever you perform any operation on ANSYS, oops, you gotta remember that all the marks beside your operation should be a green mark. If it is a yellow mark, means there is no error, but there is warning. And if it is red, it means there is an error. You can see the same sign on the workbench as well. You see, here has to be green. So before moving to the next step, you have to make sure this is on green. So on our geometry part, let's see how that. So we have our cylinder basically in here. Now that we have our pipe, we're gonna go back to our workbench in here, and let me first delete this one. Yes. Okay. We'll make sure everything is fine. Then we will go to file and save, and we will save it with a name. Remember guys, I have been telling this throughout all the years, and believe it or not, in every class I have a couple of people that they do not save their cases in the exam and they lose it. And if you lose anything in the exam due to the crash of computers, lost connections, so on and so forth, it's on you. So please, please, please make sure you save everything in every step of the way. Now, once you do that, on the second part, we double click on meshing. We'll wait till meshing opens up. Okay. Once the meshing opens up, we're going to have our geometry in here. So the geometry will be imported to our system automatically. So this side is our start, and this is the end of it. So this will serve, this side will serve. Let me rotate it the other way. Okay, and let me look at it. Okay, so let's look at it in here. This is gonna be our inlet in here, and this is the whole pipe, and this end is gonna be our outlet. Now, to create the mesh, we're gonna go step by step. So we're gonna go step by step, and what we're gonna do is we're gonna start by meshing this face, which is our start point in here. And what we're gonna do in here, we're gonna put a mesh on this. And remember, in meshing application, you're gonna work with these signs a lot. So what they are is, if you put it on this, it's gonna only select the surfaces, you see. If you put it on this, it's gonna only select the edges. And if you put it on this, it's gonna select the whole volume. And of course, this will select the vertices, which we don't have here. So put it on surface selection, put it in here, right click on it, and push insert. And in insert, no, actually select is easier one. Select this one, then go on the meshing side, then go on the then go on the meshing side, and right click on the meshing, insert sizing. Now it becomes face sizing, and if you look at it in here, so we're gonna be on face sizing, then our element size is gonna be 1.4 e minus 2. So element size would be 1.4 e minus 2 meter. And when you push any function for your meshing, the next step is you in here you generate the mesh. So let's see what happened. Okay, it generated a sort of mesh on here, and if you look at it, it looks like something like this. One thing I forgot to mention about the face meshing is to make sure to put the behavior on hard. So what this is, basically you have the option of hard and soft. When you put it on hard, you're instructing software to strictly follow these dimensions. If you put it on soft, it means that software is gonna take it as a recommendation, and if it can, it will apply your sizing. For us, we put it on hard face sizing, and the mesh is gonna look like this. As you can see here, let me move it a little bit. You see, it looks like this. Wait, in here. Okay, this is the cross section that we will see in here. So the next step is gonna be meshing along the z-axis. So if we look at it, we're gonna put some meshing along this axis. For that, we're gonna use sweep meshing. So we're gonna go on to the meshing. Here you see we were on the home meshing. Under the meshing, you see the method in here. Select the method, and in here first we have to select the geometry. Since we're gonna put the meshing on the whole 3D geometry, we will select the whole volume and apply. Then on the method, we're going to use sweep method. On the sweep side, for the source and target, we're going to put manual source and target. So our source will be the face we just meshed, and that is going to be in here. So we're going select this face as source. Source is where the copy and paste starts. Then we have to instruct the software where to end it, and where it's gonna end it is gonna be the other side, which is in here. So we'll select that one also. We'll select that one as our face. Then we're gonna go and give it a dimension, and for the dimension we're gonna use the sweep method of 4e minus 2. So this in here, we can choose the number of divisions, we can choose element size, which would be 4e minus 2. This basically instructs that in z direction how many copy pastes should happen. So let's update the mesh again. Update works same as generate basically for us. So this is gonna be our mesh. So we are pretty much done with our mesh. So let's look at our both ends in here. This is our one end. You see, since we used sweep meshing, it became more organized and better in here. Now, if you want to have boundary elements, boundary layers also analyzed, you have to put more mesh in here using inflation. But for us, it's not important right now, so we're fine with this type of mesh. Okay, so then now we have our meshing. Now the next step before moving to our actual simulation is to put the name selections. Remember, we put the name selection in there to show our boundary conditions. Now the boundary conditions that we have is this side as our inlet, this side as our outlet, and the whole here as our wall. So let's select that side. We go in here, zoom in, select this, right click, and you see create name selection. Select that and name it as inlet. Push OK. You see it creates here the name selections. Then we go to the other side. In here, then select this face, right click, create name selection, put it outlet. Okay, select the whole surrounding wall, create name selection, and put it as wall. That's it. Okay, now we are ready to move our mesh generation software, to our simulation software. But before that, I want to show you two things. One, the statistic in here. So we have 82,784 elements. If every single one of you follows this procedure, it's not still guaranteed you're gonna get the exact same number of cells, but it's pretty much you're gonna get almost the same. Now the other thing I want to show you is the quality in here. So you can check the quality, and for example you can see mesh matrix under the quality, for example the skewness. So it shows all the information for skewness, and you see all of our skewness are below 0.4, which is fantastic for us. Now next step is we go back to Workbench. First, make sure this has to be a green mark. Sometimes there is no error, and this yellow mark just shows that the project is not updated. So you push update project, and you see it becomes a green mark. Now the next step, obviously again I have to repeat that, is gonna be it's gonna be oops, it's gonna be saving your case. Now what we are doing is, oops, sorry guys, this gives errors. Okay, now we're gonna go to setup. Basically, when you double click on setup, it's gonna open for you the Fluent software, our main simulation software. So we double click on setup. Once you double click on setup, it's gonna open this window. Remember, on this window, you have to make some selections. In here, a 2-dimension or 3-dimension, of course, we're gonna go with 3-dimension. It has also detected that automatically. Always and always choose double precision. Always and always. If your responses are different from ours in the exam and it's because of double precision, you're going to lose mark. Always use double precision. It uses the utmost precision that your computer can provide. And here we have processing option. We have the option of serial or parallel. Of course, for us is serial. So push OK. Let it open. And guys, whenever this window comes up, and it comes up a lot in remote, don't select anything. Just push allow access. Okay. Now this is our ANSYS, the Fluent page. In here, it's very simple basically in terms of how it looks. On this utmost left hand column, you have the steps that you have to follow, and each step you push or double click is going to show related items on the second column. In here you're going to have the visual window, and down there are the text-based system, which we're going to show you the errors, the operations, so on and so forth. The first step you're going to have in here, always and always in Fluent, is go here on check and check your mesh. Perform mesh check. So when you perform mesh check, one thing you're going to look for is the minimum volume on your text-based system. The minimum volume should not be zero. Sorry, should not be negative. If it is negative, you're going to go back to your meshing system and perform the meshing again. If it is positive, it really doesn't matter what's the number, just positive. So make sure it is not negative. Now, on the first step is general. On the general, we're going to select some items. So we're going to select if our simulation is, let me bring this down. If our, and let me zoom this in. Okay. Let me put it in this direction actually. Okay, let me do that. Okay, now in this part, what you're going to do is you're going to basically select items on the general. It is steady or transient. Of course, it's steady, it's not time dependent, so you select steady. Do we have gravity in here or not? The question is, do we have gravity or not? And the answer is yes and no. It is yes, because yeah, in the reality of the case, always we have gravity unless we are performing some sort of simulation in space. Always we have gravity. But on the other side, it can be no, because the real question is, does it really matter for us having gravity in here? The answer is no. the pipe is full of one liquid. So as long as it's one liquid and the whole system is filled with it, you don't need gravity. So you select steady. On the solver side, you select pressure-based. Remember, guys, pressure-based solver is always used for incompressible flows, which are the 100% case in this class. If we use density-based, it means it is compressible flow. And in compressible flow, your numerical solver is also considering change in density, and that's why it's called density-based. But for us, since we are doing incompressible flow, it is a pressure-based solver. So long story short, in this class, you will always use pressure-based solver. The next part is our models. So on the model side, whatever model that we might have for our simulation are going to be showing up in here. Remember, these models are actually those auxiliary equations that we talked about them. Remember that I told you because of our computer power limitation, we cannot solve problems directly by solving our 5 equations, 5 unknowns. So what we do is we introduce auxiliary equations into the system. So all the physical models that we're going to use throughout this class are in here. But for now, we don't have any specific model. The only thing we have to take care of is the viscosity, and for us viscosity is laminar. So if we have no viscosity, we're gonna put this on inviscid. If we have turbulent cases, this is gonna be the different turbulent models, which we will be discussing it later on. But for us, for now, it is a laminar case. You push OK. The next part is material. So in the material part, we have to set the material. And remember, in here, you see the material, air and aluminum. That's by default. Any fluid in the system gonna be air, and any solid is gonna be aluminum. But we might need other fluids. So you double click on air, open a window. Now you have two ways of doing it. One, going to Fluent database, loading from there whatever liquid you want. And for us, let us see, what was it? For us, it is air. Yes, it is air. And we already have the air in here. But to tell you the truth, the name is just a name. The properties are important. So as far as it goes, it can be your own name. As long as it has the right properties, that's going to be the liquid. Now for us, the density is 1 kilogram per cubic meter. So we change this to 1. And the viscosity is 0.002. So we're going to put this on 0.002 and push change create. Once we do that, we close it. So we only have one liquid, which is one fluid, which is air. So this step is done. The next step is gonna be the cell zones. On the cell zone condition, you see here it says solid. It's just a name again. You can change it. It does that by default. The most important part is not the name. It is whether in here it says type fluid or not. So you make sure it is on fluid. Then you push edit. And on edit, again, you make sure the material is air, because it can be anything else. Sometimes you have 2-3 different fluids. So make sure this is air. Okay. This is the next part. The next part is the boundary conditions. So for boundary condition, if you look at it here, we have 4 boundary conditions. But if you recall, in our mesh application, we only created 3 boundaries. So what happened that we have the 4th one? This is an interior boundary. It has been created by Fluent automatically, and you don't need to set up anything for it. The matter of truth is the way Fluent treats everything in here, every cell in your system, regardless that it is an actual boundary or not, it will assume it is boundary. Even the cells inside the system, ANSYS assume it as a boundary, as an interior boundary. An interior boundary is a boundary that is the values of the parameters for it is being solved throughout the problem. So basically, interior boundary is not a physical boundary, it's just a mathematical boundary, and it's the way software treats other cells. All we need to take care of the inlet, outlet, and wall. For inlet, it has to be on velocity inlet, of course, because it's incompressible as we talked. And the value is going to be 1 meter per second. So we give it 1 meter per second. Push OK. For our outlet, there is nothing specific for us to do because the gauge pressure at the outlet is the pressure at the outlet is 0. For the wall as well, nothing. We just make sure it is on no slip condition because the wall is no slip condition, and push OK. Now remember that for our inlet, because I jumped it in here because we haven't still studied turbulent modeling, but the matter of truth is in here once we chose laminar, the reason in here for choosing laminar is that we have to first calculate that whether the flow is laminar or not. So how would you calculate? Through Reynolds number. And you know what the Reynolds number is? It is density multiplied by velocity multiplied by characteristic length divided by viscosity. For us in here, characteristic length is this one, 0.2 meter. And if you do that calculation, you're gonna come that you will see that, let me see if we have it in here. You will have this guide. Don't worry about that. No, we don't have it. But anyway, you please calculate it at home. You will see that Reynolds number is below 2500, which is a standard Reynolds number for transition from laminar turbulent. So if you are inside the pipe and the Reynolds number is below 2500, it's a laminar flow. If it is above 2500, it's a turbulent flow. And remember, you do not assume anything in the exam. If you want to select laminar in here, you have to explain why. You have to calculate Reynolds number and show me it is actually laminar. Okay, so you selected your boundary conditions. Here we have nothing to do. And we go to solutions method. In here we don't touch anything except that we will put our scheme on simple and this on first on this, we keep it on second order. So you can keep it on second order or put it on linear, which is the first order. In here really doesn't matter because the problem is very, very simple. But if you are dealing with a more complex problem, remember as you go to lower orders, first order as opposed to second order, or second order as opposed to third order, your accuracy is going to decrease a little bit, but your solution is going to converge, so it's going to be more stable. So if you're dealing with a complex problem, always start using lower orders solution, then build up on that going higher and higher. On the controls, we just keep the defaults as you see in here, and we go to the next part, which is the monitors. Now on the monitors, the most important one are the residuals. In here you basically tell the software, instruct the software that how long it should continue the iterations, because remember, this is a numerical method, this is a try and error. So what will happen during this process is the software is gonna start with an initial guess, which I will tell you how you will provide that initial guess to the software. Then using that initial guess, software will basically start iterating, and in every iteration it will calculate the error, and once the errors are satisfactory, it will stop the simulation. This is where you actually set the criteria. For all the parameters, the standard error is 1e minus 3. So whatever you see in here are standard. So you push again OK. Then the next step, we go to initialization. And in initialization, what you do is you are providing that initial guess to the system. Remember the numerical method, the iterative process, and it needs the initial guess. For initialization, put it on a standard initialization and compute it from inlet. When you say compute it from inlet, what it will do is, remember in initialization, you have to provide an initial guess for U, V, W, and P in all the cells in your system. So you will say, okay, what would be the most logical initial guess? And I would say the most logical initial guess is to assign every cell the data from the inlet. So you select compute from inlet, and you see it will assign to the all cells gauge pressure 0, x velocity 0, y velocity 0, and z velocity 1. So let's initialize. So once you initialized, we're ready for calculation, run calculation. But before we run the calculation, make sure you save everything. Once you saved it, you give it a number of iterations. Just give a high number because it's gonna check in every iteration by the residuals, and if it is satisfactory, it will stop the simulation. So let's start it. You see it shows the residuals in here, and it also writes these residuals in every iteration here. So we'll wait until it converges. Okay, you see it says solution complete. It is the solution is converged. Now to save this, you see right, once you go to the save, you will basically, what will you do is you will save the project. Now there are two ways of saving this. One is that you save the project, so it will be saved in Workbench. You have to again open it and so on and so forth. But sometimes you just want to save your case and data file. Case and data file are the files that you can open it just using Fluent. You don't need the whole Workbench. Case file is basically your settings for simulation. Data file is your result. So if you want to do that, you go under export, export case, it will save the case, export data, it will save the data, or export both together. Now that once you do that and we have our result, so in the exam when we say along your results submit your case and data, this is what we mean. You go export, save your case and data, and attach it to the files and upload it to the system. But regardless of that, as soon as you finish your simulation, either save the project or export case and data, because you never know. Something is going to go wrong, your computer is going to freeze, so on and so forth. You're going to lose the connection and you will lose your simulation. After you did that, now we can have a look at some results. So let's look at, for example, some velocity results. You see in here surfaces. We click on surfaces, and under the surfaces, before going to the surfaces, let's do some graphics. You click on graphics. Under the graphics, you can have contours, you can have vectors, path lines, so on so forth. So let's look at some contours. You could double click on contours. Once you double click on contours, you can select contours of what. So let's look at contours of, for example, velocity. And what velocity? You can have different velocities. Velocity magnitude, x velocity, y velocity, z velocity, so on and so forth. We want to look as the velocity magnitude, the whole velocity. And make sure this is unfilled. And then push save and display. So sorry, before doing that you have to select which surface. So let's look at the inlet. So if we look at the inlet, let's zoom in. So this is gonna be inlet, and as you can see, as expected, most of the inlet is fixed color because we provided a fixed velocity of 1 meter per second. And as it gets closer to the wall, the color turns to the blue, which means lower velocity, which is expected because remember, on the wall it is no slip condition, so it has to transition from 1 meter to 0 meter per second. Sorry. Let's look at the outlet. So let's turn off the inlet and look at the outlet. Now if you look at the outlet, it is again what you expect because it's a very long pipe. The flow by the time it reaches to the outlet is fully developed, so you have to see some sort of gradient in here. So you can have different type of contours, whatever you want on any face that you want. So in the next step, what we're gonna look at is the flow characteristics along the pipe. But this is a 3D, what we're gonna do, we're gonna make it a 2D slice in the middle and look at that. But the problem is, along the length of the pipe we don't have any surface. So what we're gonna do is we're gonna create a surface to look at the result on it. So you go under result, on top, the tab, surface, create a plane. Of course we want to create a plane which passes through the middle of the pipe, and we choose the point and normal. So in the point and normal creation method, you will give the software one point on the plane that you want to create plus the normal to that plane. One point would be of course 0, 0, 0, and the normal would be either 1, 0, 0 or 0, 1, 0. It doesn't matter because the plane in the that direction. So you create the plane, close this, go back to contours, and here velocity magnitude on plane 4, and we show that. And if we look at it, you see in here it shows very clearly from the inlet through the outlet. So let's zoom in, more zoom, more zoom, more zoom. This is inside our pipe in the middle plane. Now let's assume we want to have vectors shown up in here. So you go here, double click vectors, say velocity vectors, and it can be colored by anything. Even one cool thing about this coloring is, for example, whenever you have the temperature also, you can have the velocity vectors colored by the temperature, so showing both the temperature distribution and velocity distribution in one graph. But for now, for here, just colored it by velocity. Then select the plane 4 and save and display. Once you do that, of course you see everything goes inside each other. You have to make it a little bit visually workable. So for that, first off, put the escape on some number like 5. Let's see what happens. So what the escape does, if you put on 5, it will show every 5 cells. So it will basically disperse the vectors. The other thing we want to do, if you can see in here, the vector length is proportionate to its quantity, but we want to have the fixed length because the color already shows everything. So if you do that, save and display, you see again everything becomes big. So you have to make the scale smaller, 0.01 for example, too small, 5, yes, and bring down this. This looks like it, you see, and really there is no definite number for this skip scale thing. You have to play with it until you come up with something satisfactory, because remember, at the end of the day, whether it's an exam, whether it's your project, you have to show something that is presentable. Now, the other thing I want to do right now is to have a plot. Assume I want to plot the velocity, the total velocity along the center line as a 2D plot, XY plot. So X is my center line and Y is the velocity on it. So first I have to create a line on the center line. So what I will do is I go on the create line rake. So the starting point is 0, 0, 0. The end point is 0, 0, 8 meter, right? So you create it. Now you go to the plot part in here. So after graphics, you see plots. Open up the plot and XY plot. So you want to have the plot of velocity, magnitude on line 5, and the direction vector is 0, 0, 1, right? Because it is in Z direction. And save the plot. You see, this is going to be a plot, and this is what you expect, because the velocity at the center line changes until the flow becomes fully developed and it doesn't change anymore. And remember, for example, one question in the exam would be giving you something similar, asking you, using your simulation result, find the fully developed length. So the way you would do is you would perform the simulation, you would create a center line, then plot this, and from here approximately measure where the fully developed length is, for example, which is around 98% of the constant. So it would be around here, 0.8 meter is your fully developed. And you can have different plots. The last thing I want to show you are the reports. So if you go to the reports, it will report you many things. So under the report, you can report, for example, fluxes. What would fluxes would be? For example, what's the mass flow rate at the inlet? Let's select compute. It shows the mass flow rate at the inlet. What is at the outlet? You see almost a negative of that, and there is one very small error, which is natural because you have numerical errors. That's fine. So you can have different fluxes in here. Or you can calculate surface integrals, meaning, for example, what is the area weighted average of velocity at the outlet. So all the averages are being calculated here, and you see average is almost 1. It's not 1 exactly because again there are errors, but it's very close to that. So any averages are under surface integrals, the fluxes, the vectors in here, sorry, the vectors under the graphics, and also the contours. So that's it, guys, and please I'm asking you, first listen to the whole thing, try performing it before the class, then in the class, during the class on Friday, you can ask about if you have any question about it. Thank you very much, guys.